So I'm Ivan Grahek. I'm a postdoc with Anitai Shenhav at Brown University. And so today I will talk about our recent project looking into reconfiguration costs of cognitive control adjustments. So cognitive control is a set of processes which allow us to flexibly adjust how we process information in order to reach our goals. And more specifically, it allows us to adjust what we process and how we process it with which intensity. And computational models of cognitive control posit that we can think of control as a decision-making process, which is based on weighing the costs and benefits of allocating control in a specific way, and then we can maximize value and find what optimal allocation would be. So in this talk, I will focus on cost of control, and there are different types of costs. The most intuitive ones are intensity costs. The more control we allocate, the harder it is, the higher the cost. Then we have opportunity costs. If I'm focused on one task, there are many other things I'm not doing at that moment. But the costs I want to focus on in this talk are reconfiguration costs. And these costs are commonly studied in task switching literature. So these are the costs when you're doing one task and you need to switch to another task, you incur a switch cost. However, in this project, we're interested in something a little bit different. And that is the situation in which you're only ever doing one task, but what you need to adjust is control intensity, how you're processing information. So, for example, your goals change, you need to complete the task faster, or you have an increase in motivation. So the usual suspects here of different control adjustments would be increasing your levels of attention or increasing your levels of caution in these situations. And previous speakers have already introduced the drift diffusion modeling approach. So from this framework, the sort of speed at which we accumulate evidence would be akin to attention. That would be a drift rate. And then we would have a threshold, the boundary, how much evidence we need to make a decision. That would be akin to caution. So then the question is, now we have this two-dimensional multivariate space of control signals formed by threshold and drift rate, and how do we find optimal points within this space? So previous work from our lab, led by Jason Lang, built on work by Rafa Bulgac, proposes this fairly simple reward rate-based model that can do so. So we consider payoffs for a specific combination of drift rate and threshold. We can calculate the probability of being correct or incorrect. That might be tied to some incentives in the task. We get a payoff. Then we have the time it takes us to reach a decision, non-decision decision time. And then we have some intensity cost in this model on the drift rate. So the thing with this model is that now we can find optimal levels of drift rate and threshold given certain environment with different incentives by maximizing the expected value of control here. And we can find a certain optimal point. So the question that we have here is, what happens in situations in which people need to navigate this space, when they need to adjust where they are in this space and they need to move around? So you can imagine situations in which you have to perform a task accurately or to perform it very quickly, and you can play this game and find optimal points here. So for example, if you need to be very accurate, maybe you'll have a high threshold and a high drift rate. If you need to be fast, you'll have a low threshold, maybe a lower drift rate, or something like that. So then on the other hand, we have these situations in which we need to move around in this space. Maybe we wanted to be very accurate, but now we need to be very fast. So this would be a situation that has high reconfiguration costs relative to the previous situation in which you perform in one condition and then in the other. So how can we adjust this model now? First, we need to consider multiple conditions, because now we're moving in this space. So we need to be optimizing across multiple conditions. But crucially, we wanted to add reconfiguration costs here. And these reconfiguration costs would be some function of the distance between the points through which you're moving. Here we use exponentiated Euclidean distance. We can get into the details if someone is interested. But the crucial insight here is then the optimal solution with the same levels of goals or incentives, the optimal solutions would be pulled closer together, because we're assuming that there is this cost on movement through this space. Okay, and then this framework allows us to test these predictions empirically. So I'll first give you a flavor of the broad paradigm, and then I'll get into two experiments. So what we're doing is we're giving people different performance goals or different incentives with different cues. Then they have a fixed time interval during which they perform a Stroop task, and it's self-paced. They can perform as many trials as they wish during a fixed time interval of about 8 seconds. And then they get some feedback related to their performance. So the crucial manipulation here is that we have some blocks which are fixed. You always have one condition that you're performing. For example, you're always focused on speed. And this would be the situation with no reconfiguration costs. Then you have varying blocks in which you need to be moving in this space. So switching between, for example, speed and accuracy conditions. Those would be the varying blocks in which the optimal solutions would, according to our model, be pulled closer together. So in experiment 1, we did the simplest thing possible. We induced different performance goals, kind of the standard in DDM literature, tell people to try to be really fast or to try to be really accurate. So we have these fixed and varying blocks. In varying, we sometimes focus on speed, sometimes on accuracy, and in fixed, we're always doing one of them. So then we can simulate from our model and look at the predictions from the model. So if you look at in the x-axis, we have threshold and drift rate. And here what I'm plotting is the difference between accuracy and speed. So the first thing you will notice is the model predicts that people will have higher levels of caution, higher thresholds, and also higher drift rates in accuracy relative to speed conditions. This is something that we would expect. But the crucial prediction here is this difference between fixed and varying blocks, where this effect of performance goal on threshold will be reduced in the varying case relative to the fixed case. So it will be reduced when people are moving between conditions. And then we can fit a DDM to our data and check whether these model predictions pan out. So this is what our data looks like. Here I'm plotting, so this is fit with with Bayesian hierarchical models. So I'm plotting the difference between the posteriors in accuracy and speed case. And what you see indeed for the threshold, we see this difference for both threshold and drift rate in accuracy over speed. But we crucially see, especially in threshold, this reduction on the influence of performance goal on threshold between varying and fixed blocks. Okay, so what this tells us is we have found some evidence for these reconfiguration costs that work purely on the control intensity side and not when you're switching between different tasks. However, we have induced this movement through the control space in kind of a very explicit manner. So we also wanted to try to see what happens when we do it a bit more implicitly and a bit more voluntarily. So we used a paradigm in which we push around people through this space only by giving them different incentives. So we use a very simple 2x2 design. In this task, it looks the same as the previous one, but now the cues are sometimes you can get high or low rewards, sometimes you can get high and low penalties tied to your performance on a given interval. So we can play the same game. We can now look, for example, at the effect of penalty on cognitive control allocation between blocks where penalty is always fixed. So for example, in this case on the left, you always have these like low bounds which signal you won't be losing a lot of money. And you have other blocks in which penalty is varying. So one incentive is always held fixed, one is always varying. And now the thing that we can do is look at the model predictions about the influence of penalty on control in this task. So what the model predicts here, similarly to previous work from our lab, when you look at penalties, the main prediction is that if you expect high penalties, you will increase your threshold. That kind of makes sense. You increase your levels of caution relative to low penalty case, and then you also increase the drift a bit. So that we did expect, but the sort of crucial thing here is that, again, particularly pronounced on the threshold, we're predicting lower effect of penalty on threshold in varying relative to fixed blocks. And when we look at the data, indeed, it pans out. So we're seeing this reduced effect of penalty on threshold in varying relative to fixed blocks. And we're seeing a trend in drift rate, but it's not significant. By the way, these are 95% credible intervals from the posteriors. And then finally, we can also look at the same thing for the effect of reward on control. So we can compare blocks in which reward is varying and in which it is not varying. And again, the prediction here, the main prediction in the model is reduction of threshold, because again, you're in this self-paced task. So if you're optimizing for reward rate, you want to go faster to do as many trials as you can within an interval. So you have a reduction of threshold in high relative to low reward intervals. But again, the crucial prediction is that this effect will be attenuated and varying relative to fixed blocks. And indeed, this is something that we find in our data. Okay, so across these two experiments, what we seem to be finding are these reconfiguration costs on adjustments within a single task. And we believe that these reconfiguration costs can serve the purpose of regularizing the movement through this abstract 2D space of potential control signals that you could be employing. And this provides support and further extends some of the computational models of cognitive control, which include reconfiguration costs. And importantly, and I have focused here on these experiments that promote threshold adjustments, these sorts of costs on adjusting threshold is something pretty novel that we have found. Commonly, these threshold costs come up by regularizing opportunity costs. But here we also find costs on adjusting thresholds. However, we have done 5 experiments with different environments here, and I didn't have the time to present all of the data here, but I have presented environments that promote threshold adjustments, so when you have penalties or when you're focused on accuracy, but we have other environments in which you, for example, vary reward and actual outcome contingencies, which promote large adjustments on drift rates. And then again, on the drift rate, we do see these reconfiguration costs. And so this is not just kind of a theoretical story. We think that this is also very important for how we measure incentivized cognitive control. So commonly in the field, we do have these designs where if we want to look at how reward influences, say, cognitive control, we'll have these designs where reward magnitude varies on trial by trial. And importantly, our work sort of indicates that your effect of reward on control will be sort of contaminated by these reconfiguration costs. So if you're, for example, studying individual differences and you want as clean effect as possible of incentives on control, you might want to use these designs that reduce reconfiguration costs. And further, we're also interested in looking more into these reconfiguration costs in relation to individual differences in aging and psychopathology. And then finally, we cannot go deep into the mechanism of where these costs are coming from with these designs, but that is something that we're interested in. And specifically, the question of whether the optimization of these costs is a proactive or reactive mechanism. And in our current designs, people are aware that in the coming block, they will have to keep switching or not. So it might be proactive. But also in the current data, we have, if we look at switch repeat analysis, which I can get into if someone is interested, we do see that we see these classical switch costs, which might point into the direction of kind of a reactive mechanism. So this is something that we're very interested in exploring more. And yeah, I just want to thank my collaborators. Jason Lang has co-led this project with me. We've been advised by Amitai Shenhav, and Mahalia Prater-Fahey, Debbie, and Romy Fromer have all worked on different incentivized cognitive control studies, and we have used some of their data for this project. And yeah, thank you for your attention. Okay, so maybe we can start with the audience. Yeah, if you could just go to the mic because of the virtual audience.
Hey, very nice talk. I had a question about the task you use. You seem to have used like these stop signal, no-go, no-go, no-go tasks primarily. Have you used any other type tasks, or can you explain the motivation for using a stop signal, especially when fitting a DDM to that type of task isn't always as straightforward as fitting it to an alternative forced choice task?
Okay, yeah, maybe I didn't explain well, but we use the Stroop task here.
Yes.
Yeah, so it's not a go no go, it's a Stroop task. So that's what we went for.
Cool.
We use it just because it's kind of like a flagship cognitive control task. And we do a lot of work with it in our lab. We kind of stuck with the Stroop, but we are interested in using some similar conflict tasks, for example, flanker task and things like that. Yeah.
Cool.
Fitting DDMs is not like super straightforward here. You have to do some things, but it's not as difficult as it would be in the subsignal.
Very interesting task. I was wondering, so I didn't understand if you assume that this regression between the two extremes are the drift rate across the whole task, or maybe you can find evidence for this in the between trial variability and drift rate. I don't know if you fit this parameter, but I wonder if you find differences, which would be quite interesting because I know it's having an effect that haven't been found yet, significant effect in the data. So it would be interesting to see this kind of effect between those two conditions.
Yeah, this is something that we're interested in. We haven't done it yet. So we have done only the kind of like simple fitting and comparing between different conditions. But indeed, as we move closer to what is the mechanism through which this is happening, this is something that we would like to explore. So basically the idea is, and if you're able to do trial by trial, you could get at that. The idea is, are you proactively deciding, okay, in this block, I'm going to be switching a lot, so these will be my optimal points? Or am I holding optimal points as they are normally, but I start moving towards them, but I don't manage to reach it because I sort of run out of time in preparation? And indeed, if you start looking at trial by trial adjustments, you could potentially get into that.
I don't think you need to look at the trial by trial, but there's a parameter of variability of drift between trials. So if you don't find a difference between these, you can say that maybe they can kind of find a drifter that fits all kind of trials. But if you find that the variability is larger, and that means that they might switch in between those drift rates, and this will be accounted by a larger variability.
Right. Yeah. I would be interested in talking a bit.
Sure, I'll cut you out.
Thank you.
Hi. Thanks for the nice talk. So I have actually many questions about the cost. So first of all, so the formula for the EVC is simple, in this mathematically simple. So am I right in assuming that it's some kind of probably linearization of some more complex cost that maybe we don't know? And I also wanted to ask if you could explain a bit more what you put in the reconfiguration cost.
Yeah, so this is, so I just had like a kind of like a high level model there. So I can briefly spend maybe a minute on what the model actually looks like. Let me just see where the pointer is. Okay, so in the model, the sort of payoff part is you have the probability of an error for a given drift rate threshold combination. And so this is the probability of being correct, one minus error. You have some weight on that. So when we're simulating that, would be some like rewards that you're getting for being correct. Then you have another weight that would be like penalties, for example, in that incentivized version. You have the DT and non-decision time here. The intensity cost is in the original model. So in the original Bogach model is just this. Then my colleague Jason Lang added this term, and it actually shows that it fits data really well, because otherwise, if you don't regularize drift rate here, it explodes because it's always optimal to allocate maximal, because threshold is kind of tamed by this, but not drift rate. So you have the intensity here. And then so for the reconfiguration costs, we sort of, when we started doing this work, we explored different types of regularization here, like L1, L2. In the end, what I'm finding so far is that as long as you have some form of regularization there, you can capture the qualitative patterns. And we don't have the power in this data to really now start dissociating between different types of costs. What we went for here in the original computational implementation of EVC by Sebastian Muslik, he had these reconfiguration costs on the drift rate that was exponentiated Euclidean distances. In his case, that was only drift rates. It wasn't 2D. So we kept the same thing to kind of be in line with the previous model. But basically, you have the exponentiated Euclidean distance between the drift rates and thresholds for the two conditions, and you have some weight on there. So that's what the model actually looks like. And you're then summing over different conditions. In our cases, you mostly have two, but you can. This is kind of a general form where you can extend it to more. And you have some weighting by the probability of their occurrence, which in our case is always 50-50 when they're varying. So that is, yeah, I hope that kind of addresses the question. And then, sorry, I forgot the second one.
That was the second one. The third one that is, possible to relate that to what's actually happening in mechanistically, that's for like reorganizing neurons?
Yeah. So I mean, the sort of simple way to think about is if you think about like in neural network terms, you have some activity patterns that correspond to one or the other state, and you're sort of moving from one attractor to another. However, that is still very high level. And we're currently not thinking at the level of SDN for threshold or something like that. In terms of drift rates, it's quite more straightforward. You have some gain over the visual cortex that's like signaled by ACC-DLPFC or something like that. But currently, this project is not at that level. We are hoping to maybe start doing some like EEG, maybe get at this attractor state or something like that. But currently, this is the data we have. And maybe we can just quickly check in if there is maybe one online question, and then we have to move on.
Yes, we have one question. It's from Tobias Ludwig, and it's asking if you use a strobe task, are there two types of switches between color, word, and between speed and accuracy? Do they interact somehow, or are the effects of reconfiguration purely additive?
That's a great question. That is something that we have not explored so far, because you would need a lot of data for all of the different switches between colors. Now the colors are sort of pseudo-randomized, so they don't repeat much. So the current idea is that we're at least averaging out that effect. But that is not something that I think we can look at with the current data. We just don't have enough power. I would imagine people definitely do still have to switch attention from one color to another. So it is potentially interesting. We just haven't looked at that yet.